Welcome to part 4 of the first tutorial. So in this tutorial, we'll discuss the Pandas package. Let's get started with the Jupyter notebooks. Previously, we looked at numpy. So Pandas is a package that builds on top of numpy and provides high-level data structures. And we'll look at some of these data structures. To get started with, let's create a numpy array. And before that, let's import pandas as pd and import numpy as np. Now let's create a numpy array that contains 3 rows, and each row is enclosed within a list, and there's a list of lists that represents 3 column matrix. And let's run this cell. So our array contains iron 25, 7.8 in the first row, lithium 3.5 in the second row, aluminum 13 and 2.7 in the third row. Now let's pass this array to a class called dataframe. So dataframe is a class within Pandas, and let's see how a dataframe looks like. So as soon as we run this, we see an Excel sheet like structure printed here, and the rows are named 0, 1, 2 and the columns are also named 0, 1, 2, and this is basically a prettier way to look at array as of now. Now we can change the names of these columns. When we define a data frame, we can do that by providing our array to the data frame class and then providing a keyword called columns and providing one string for each column. So we have 3 columns. So we provide element, atomic number and density as the names of these 3 columns, and we pass it as a list to the keyword columns. Now if we rerun this, we see that our data frame has columns named element, atomic number and density. Now we can also name the rows of the data frame. The rows of the data frame are termed as indices. So whenever we define a data frame, just like we provided column names in a list, we can provide the row names or the index names in a list, and we need to provide this to the keyword index. And as we run this, we see that the rows are named dp1, data point 1, data point 2 and data point 3. Now just like we can access elements of an array or a list, it's essential that we also are able to access elements of a data frame. So now let's try to access 2 entire columns of a data frame. So we have the column element, atomic number and density. Now let's try to access the column element and atomic number. So what we basically have to do is provide the names of these columns in a list. So this is a list, and then pass this within square brackets just to the right of the data frame name. So the data frame name is df. We start square brackets, and within a list we provide the name of the columns that we want to access. So if we run this, we get a part of the data frame. Now we can also access a single column. So let's get rid of one of the column names. And we see that we have passed element, the string element, that is name of the column, within a list within this square bracket, and if we print this out, we get a single column. Now note that we can also directly pass the name of the column without putting that in a list. So here element is in a list, but we can remove it from the list and just provide element within square brackets to data frame. And if we print this out, we see that this is a bit different from the previous print statement, and the difference is that, so if we print out the types of both the previous the previous data type and this data type. So the first one is element within a list passed to data frame. If we get the type of it, it is a data frame. So it's pandas.core.frame.data frame. But if we do not pass it within a list and print the type, this data type is called a series. So it's pandas.core.series.series. Series are basically a slightly higher version of numpy 1D array, and it can only contain a 1D array, whereas data frames can contain matrices as well. So every row or every column of a data frame can be accessed as a series. Now we can also, we saw how to access columns, we can also access rows. So that is similar to accessing columns, just that we do not pass the column name directly within the square brackets. We use the method called .loc, that is .loc, and then we start the square brackets, and then we can provide our row names directly, a single row name which will return us a series, or we can provide multiple or single row names within a list that will provide us a data frame. So let's look at this cell. So we call df.loc and we provide dp2, that is name of a row. Let's print the df out so that we have a reference here. Yes. So dp2 is this row, and if we provide dp2 within a list, we get this data frame. But if we directly provide dp2, we get a series that contains the elements of this row, lithium 3 and 0.5. Now notice that our row names have been changed, or the indices have been changed to dp1, dp2, dp3. It might be useful sometimes to access a row by its index number. The indexing is similar to lists or numpy arrays. So say we want to access the first index of this data frame that corresponds to dp2. Instead of providing the name of dp2, we can also provide the index, but we, instead of using loc, we have to use the .iloc method. So if we call df.iloc and provide the index, it gives us the same series as before, so corresponding to dp2, and again if we provide this as a list, we get the data frame, and we can access multiple rows here as well. But note, another important thing to note is that if you are not providing a list, you cannot access multiple rows or columns. So if I run this, it basically gives me out the index, the first row index and the second column index. So that basically corresponds to, this is zeroth row index, this is first row index, and this is first column and zeroth column index, first column index and second column index. So if I do iloc 1, 2, I get this first row and second column, that is 0.5. So I get back 0.5 here, that is accessing a specific element within a data frame. Now we can add new columns to our data frame. So let's again print this data frame out. So we have only 3 columns, element, atomic number and density. Let's say we want to add another column named symbol. So we can just name this new column within square brackets. So we just call df, and within square brackets we provide symbol, and we provide a list that we want to pass to this column. So because there are 3 rows, we provide 3 elements in the list, 3 strings basically. So as we run this, we see that there is an additional column added to data frame symbol that contains fe, li and al. Now we can also create data frames starting from dictionaries. We saw how to create data frames from arrays. Now let's say we want to create a data frame starting from a dictionary. So we create that dictionary. So this is the first key of the dictionary, element, second key is atomic number, third key is density, and fourth key is symbol, and each key has a value, sodium, 11, density and Na. And we just take this dictionary and provide this to our data frame class. So pd.dataframe, we provide this dictionary, and if we want, we can provide an index as well. So if you notice that this dictionary, so let's print out this dictionary here. This is how it looks like, and there is just one row in this dictionary, so we can provide index as some string. So let's provide this as dp4 and store it as df underscore. So if we run this, we get dp4, sodium 11, 0.9 and Na. This is another data frame created from a dictionary. Now let's say we have two data frames and we want to concatenate them, convert them into a single data frame. So that can be done by using the function pd.concatenate, and then we have two data frames. So our df underscore is this dp4 sodium 11.9 Na, and our df is this. So let's say we want to add the last, the df underscore to the end of df. So we can do that by providing both the data frame objects within a list. So in a list we provide df, that should come first, and df underscore, and then we say to which axis we want to add the new data frame. So we can add this new data frame as a column or as a row. Now because both our data frames have same column names, the second data frame should be added as a row in the first data frame. So we mention axis is equal to 0, that means concatenate both the data frames using rows. So if we run this, we see that both the data frames have been concatenated row wise. And we can maybe return, so this function returns a data frame, but none of the data frames themselves would have changed. For example, df has just 3 rows now, df underscore has 1 row. So let's return this data frame. Let's replace df with this new concatenated data frame and then print df out. So now df has been updated. So let me get rid of df underscore. Now we have our index names as dp1, dp2, dp3, dp4. What we can do is select a column and set it as the index. For example, if we run this df.setIndex and pass it a column name and set in place equal to true, that means whatever changes are made, do it within data frame, do not provide me a new data frame without changing df. So if we do this and we print out df, we see that now symbol has been set as the indices. Now if you want to redo it or undo this, so you can type df.resetIndex, and because this is a method I have to provide brackets here, and then so if you just run this, we get, so whatever was there is undone basically. So symbol again becomes a column here, but again this should have this in place tag. So let me show you what happens without in place equal to true. So if I create a new cell and I print df out, we see symbol is still set as the index of the data frame, because df.resetIndex provides a new data frame and it does not change df. But if we make in place equal to true and run it and then run df, so the changes has been made in the data frame itself. So that's what in place equal to true means. Now we can access the indices like this. If we pass df.index, it states us what the indices are. So basically now it returned a range index object that says the index starts from 0, stops at 4, so 4 is not included, and it's in steps of 1. So it is similar to the np.arange function where the second argument is not included. Now if we just rerun this and we set the index as symbol and then we run this df.index, it basically provides us all the names of the indices, that is fe, li, al, na. Now again we can access indices based on these names of the new indices. So let me print df here. So this is our new df, and if we want to access the fe row, we can use df.log, and within list we have provided an fe, so that should return us a data frame. Now let's compare data frames with numpy matrices. So we looked at how numpy matrices can be made using np.array. So these are basically nnumpy nd array objects, and we also saw how we can multiply two matrices using the dot method. So let's create 3 matrices. So matrix 1 is a 2 cross 3 matrix, matrix 2 is a 3 cross 2 matrix. So clearly a 2 cross 3 and a 3 cross 2 matrix can be multiplied. So let's take a look at these two matrices before we perform the multiplication. So mat 1, it's a 3 cross 2 matrix, 3 rows and 2 columns, and mat 2 is 2 rows and 3 columns. We can multiply these two matrices. So we just have to type mat 1 dot mat 2, and this is basically matrix 1 into matrix 2. And note that what the star mark or the usual multiplication does. So let's print out mat 3 as well here. So mat 3 has same dimensions as mat 1. It is a 2 cross 3 matrix, and if we clearly mat 1 and mat 3 are not multiplication compatible, because this has 3 rows and this has only 2 columns, they cannot be multiplied. But what happens if we just directly do mat 1 into mat 3? This basically performs what is called a Hadamard product. That means it multiplies numbers element wise. For example, 1 here gets multiplied by 6, 2 gets multiplied by 4, 3 gets multiplied by 8, and so on. So in some machine learning codes we will use the Hadamard product, so it's important to know what the usual multiplication sign does. And now let's convert these matrices into data frames. So we have matrix 1, matrix 2, matrix 3, we have converted them into data frame by passing them through pd.dataframe, and we have stored them as df1, df2, df3. Now data frames are actually matrices, so we can use the dot method to multiply two matrices as data frames. So our mat1 dot mat2 is this, and if we do the same with df1 dot df2, we get the same matrix. So that is 7, 10, 15, 15, 22, 33. It's the same thing. So data frames are also like numpy and darrays, and the same a lot of functions that you can use with numpy and darrays can also be used with data frames. Again, we have data frame 1 and data frame 3. Let's try to do the Hadamard product. So this is the result of Hadamard product of two matrices. If we run this, we get the same thing. So it is 6, 14, 24, 36, 50, 66. Here also it's 6, 14, 24, 36, 50, 66. So this is our previous data frame that we created. Because it's a matrix, we can perform scalar multiplication with it as well. So what do you guess will happen if we do df times 2? So the interesting thing here is iron, lithium, aluminum, sodium are not floats or not integers. So let's see what happens if we multiply this entire data frame by 2, and let's print this out. So we see that iron repeats twice, lithium repeats twice, and the same happens with 25 as well. So instead of returning 50, it returned 25, 25. So with this, what can you guess about the data type for each element in this data frame? So clearly these are not integers. Turns out these are strings, basically because we initiated our starting array with with mixture of strings and integers, and turns out it becomes integers when you provide these mixtures directly. So what you can do is test out what happens when you multiply two strings. So let's say we have iron and we multiply 2 to iron, so it returns iron, iron. So basically all these entries are strings here, that's why this happened. However, if we have actual numbers in our data frames, just like in df1 say, so if we repeat this with df1, so let's print out df1 first, this df1, and if we do 2 times df1, we see now this follows the usual multiplication rules because we have integers in our data frame. Now let's go to the apply method. So this is a very important method and very versatile method within data frames. Let's see what happens here. So first let's print out our data frame df and say we want to add another column to this data frame that has the name nickname, and what we want to do is provide the first 3 letters of each element as the nickname corresponding to that row. So if there is a string, say aluminum, and we want to access the first 3 letters of aluminum, the indexing is similar to lists. So basically we can say I want index 0 to index 4. So the last index is not included. That's why it prints out 0th index, first index, second index and third index. So 4 is not included. So we get ALUM, that is the first 4 characters, because indexing starts with 0, we get the first 4 characters of aluminum. Now we want the first 3 characters. So if we do this, this is how we get the first 3 characters. Now we create a function. We already looked at functions. So this is our function that takes in a string. The function is named getNickname. It takes just one argument, that is x. X should ideally be a string, and what it returns is the first 3 elements of x. So we can skip this 0 in aluminum here. That means that it defaults to starting with 0. So this getNickname function returns the first 3 characters of a string. Now what we can do is basically we want to run this function to input iron in the first row, lithium in the second row, aluminum in the third row and so on. So let's first create a series that has these element names. So we can do that by doing df and element, and we have to provide this within strings. So this is our series. Now every series has this dot apply method. So this is a regular method within the series class, and the input to this dot apply method is a function. So we have this getNickname function. If we provide this function here, let me run this function first, because before running this function, Python does not know that this function exists. So we define this, and the apply method takes in a function. So we just write getNickname. So we have already defined this function. That's why when I press tab, we can autofill this. Now how this apply works is it takes each element of this series and provides it to the function, and whatever is the return value of that function is then passed as a new series. So let's run this. So our element df element is iron, lithium, aluminum, sodium. If we use the dot apply method and pass this function getNickname and run this, it returns another series where all the elements of the series are basically the return value of our function that we have provided, and that happens element wise in the series. So the first element was lithium, so the first element was iron. So the indices are as set in the data frame, Fe, Li, Al, etc. So the first element was iron. So getNickname takes iron, returns IRO, and that is the first element in the returned list. So if we want to create this new column within our data frame, what we basically have to do is use this dot apply method and store the resulting series in the data frame as a column named nickname. So df within square brackets nickname is a column within data frame, and we return the series that we get using the apply method to this column. And if we again print this data frame, we see that there is a new column named nickname, and that has our desired characteristics. So IRO, LIT, ALU, SOD, etc. Now the next thing is sorting values. So we can use dot sort values method and provide the name of the column use or the row, we can sort values using rows or columns. So let's say we are sorting these rows in descending order of the density. So the highest density should appear as the first row. So we can use df dot sort values, and to the by keyword we provide a list with the name of the column using which we want to sort, and then we provide what we want to interchange. So if we want to sort things column wise, we want to interchange the rows. So that means we have to provide axis equal to 0, and ascending false means it sorts the values in descending order. If we set this as true, the values are sorted using ascending order. So if we run this, okay, we get an error. Yes. So the reason for this error is the densities here are actually strings. We saw that previously, and strings cannot be sorted using the sort values method. So first what we need to do is convert the densities into integers. So one way to do that is, let's use the apply method. So let's say df density is equal, and before that, for simplicity, let's define a function called convert to float. So we want to convert these density strings into floats, and we provide a string here, and the function should return, the function should basically convert the string into float. So this is our function, convert to float, and then you want to apply this to every element of density. So let's do df, then density dot apply, and then we pass this function, convert to float. So our density should have been converted to float values now. So the sort values function should work. So let's run this now. Yeah. So now it knows how to sort floats. That's why this function does not throw an error now like previously. And now we see the rows are arranged in decreasing order of density. Again, this sort values returns a new data frame. So if we print df here, the order here is different from the order that we returned. So if we just provide in place equal to true, it makes changes in the data frame and does not return a new data frame. That's why we do not see anything printed out. But we again reprint data frame, then we see the values are sorted by density. Now we can also sort values by indices. So for example, if we want to sort values, so okay, let's sort this by say fe, and we want to now sort values by this index fe, and we have set axis equal to 1 because we want to interchange columns here. And if we run this, we again get an error. The reason is not all elements in our data frame are numbers which can be sorted. So there are strings here. So again let's try another thing. So just as we converted atomic density into numbers, let's convert atomic numbers into floats. So let's do df atm dot no dot, and then use the apply method to convert atomic numbers to float as well, dot apply, and convert to float, and let's print our data frame out. Now let's create a subset of this data frame that contains only atomic number and density. So to do that, let's rename the new data frame as df underscore, and we want a data frame. So we have to provide the columns name within a list, and it's atm.no. comma density, and let's print out df underscore here. So this is how our df underscore looks like. Now if we want to sort values by df underscore, and we want to do it in an ascending order. So by default ascending is false, so we need not provide this, but for clarity let's do this. And if we run this now, we see densities and atomic numbers have been interchanged because they have been arranged in ascending order. So densities are lower in our case, and we do this only for the first row, and whatever changes are done in the first row are applied for every row here. So that's how sort values works row wise as well. Now the next important thing is importing data as a data frame. So so you'll find this mechanical props kaggle.csv file in the course material. So you have to put this CSV file in the directory in which you are running the Jupyter notebook. So for example, this is the directory where I am running my Jupyter notebook, and mechanical props kaggle is in the same directory. So we can use pd.read CSV. So CSV is the format of this data, and we can import this as a data frame. Now let's print this out. So this is a huge data frame basically, and if we scroll all the way down, we see there are 1552 rows and 16 columns. So we have our data frame, and you can click here to get more information about what the columns mean. So there's a column named STD, a column named ID, material, heat treatment, SU, SY, A5, etc. So here are details of what these mean. So STD means standard, then ID means unique identification code, then there's material name, then there's heat treatment method, ultimate tensile strength, etc. And this data is taken from the website called Kaggle that has a lot of open source data for machine learning purposes. So let's see how we can analyze this data using Pandas data frames. So we can use the df.columns attribute to access all the columns. So these are all the columns we have in our data frame, and we can use the .info method to find out the type of data in each column. So if we use this, we see all the column names are mentioned. It says 1552 entries, basically there are 1552 rows, and for example the first column STD has 1552 non-null values. So non-null values are values that are filled out, these are not empty. And the type is object. Object basically means it's a string in the data frame. So STD is a string, ID is a string, material is a string, heat treatment is a string, but SU column is an int64, it's basically integers. So if we go to the data frame and see, clearly the first 4 columns contain letters, so they are likely to be strings, but the SU column, SY column, A5, etc., they look like numbers, but again we saw that numbers can also be strings, so we confirm that with the .info method that these are actually numbers. So some are int64, some are float64, etc. And it also says how many null values are there. So for example, with STD there are 1552 non-null values, so there are no empty entries here, whereas with heat treatment there are only 802 non-null columns. Basically the rest do not have an entry here, they have null values. Now we can also use the df.describe method. So what this basically does is returns a data frame. The indices are some values like how many entries are there, how many non-null entries are there, what are the mean of these entries, standard deviation, min, and then quartile, the second quartile, third quartile, etc., the max value. And that is returned for every numerical column. So for example, SU, SY, A5, etc. are all integers or floats, whereas STD, ID, etc. are strings. That's why these cannot be calculated, and hence these are not returned in the .describe function. And yeah, we can access few of the columns here. So say we have access SU, A5, BHN, E, and we use the dot sum method. This basically should return the sum of all the values in these columns. So these are the sums. This to show you that there exists a method called dot sum. And there's another important method called dot is null. So if you run this, it again returns a data frame where the data frame is called a mask because it only contains true and false values. So every entry that is null has a value of true. For example, in the first row, we see pH has a value of true, and if we go up to the data frame and we look at the first row, pH, we see there is NaN. Basically there is no value here, that's why there is true, and all the elements that are filled out will have a value of false here. So this is how is null works. Now say if you want to find out how many null values are there per column, so every false is treated as a 0 and true is treated as a 1. So to this data frame, if we again use this dot sum method as shown here, so this will tell you column wise how many null values are there. So for example, in heat treatment there are 750 null values, because for every null value there is a true, and true are treated as 1. So we sum them up column wise, so we get 750 here. So multiple rows do not have null values, but a lot of them have null values as well. For example, BHN has 1089 null values. Now we can also do something called conditional filtering. Say you want to find out all the rows within the data frame that have an SU value of less than 100. So let's see this in two parts. So DFSU brings out a series. So this is our series. If we do this, so DFSU less than 100, this gives us a masked series. Basically it has true and false values. If the SU value is less than 100, it returns a true. If it's greater than 100, it returns a false. Now we can provide this masked series. So let's call this masked series and run this. And if we provide this masked series to the data frame, so our data frame is DF, and within square brackets we pass this masked series. It basically returns all the rows that have value true. That means it returns only rows that have a SU value of less than 100. So this is the data frame that we got, and notice that we just have 1, 2, 3, 4, 5, 6, 7, 8. We just have 8 rows. Basically means there are only 8 rows that have SU value less than 100. And if we check here the SU values, indeed all of them are less than 100. So all of this is done in a single line here. So basically this is our masked series, DFSU less than 100, and we have provided this directly to the data frame. So if we print this out, we get the same result as above. Basically all the rows that have values less than 100 in SU column. Now we can also find unique labels within a column. So for example, we have this column std, and we see there are strings ANSI, etc. We want to find out how many different strings are there in the actual data frame. So this is the masked data frame. This does not make any change to your real data frame. And if we run this dfstd.unique, we see we get 1, 2, 3, 4, 5, 6, 7, 8 values. Basically there are 8 different types of strings in the std column. So we got this by using .unique, and we can use the .nunique method to find out how many number of unique values are there. So there are 8 unique values here. So that's how these work. So this is what we'll cover for now using Pandas, and if we come across anything new, that will be discussed with you while we discuss further codes. Thank you for joining, and I'll see you in the next tutorial.